Hello, myself Dr. D.K.Shedge, Professor in Department of Electronics and Telecommunication Engineering, AISSMS Institute of Information Technology, Pune. I am going to show here how to find out the Fourier transform of some elementary waveforms. The Fourier transform of any arbitrary function x of t is given by x of omega equal to integration from minus infinity to plus infinity x of t e raised to minus j omega t dt, and its inverse Fourier transform is given by x of t equal to 1 upon 2 pi integration from minus infinity to plus infinity x of omega e raised to j omega t d omega. Of course, for finding out the Fourier transform, x of t must satisfy Dirichlet conditions. Let us see how to find out the Fourier transform of the exponential function e raised to minus at. This function is e raised to minus at u of t as its plot shows, because e raised to minus at it is existing from t equal to 0 onwards on positive side. A is a positive number here, its assumption. So its a Fourier transform can be found out from equation of a Fourier transform. That equation was written as analysis. F of j omega will be given by integration from minus infinity to plus infinity. F of t e raised to minus j omega t dt. There f of t we can substitute as e raised to minus at u of t, and to take into account u of t will have integration from 0 to infinity. So it will become integration from 0 to infinity of e raised to minus of a plus j omega t dt. And we can find out very easily this integration of e raised to minus of a plus j omega t dt. Its integration will come out to be e raised to minus j omega t divided by uh, minus of a plus j omega, with upper limit infinity. That term e raised to minus of a plus j omega t will become 0, and with lower limit it will become plus 1. So answer will come out to be 1 upon a plus j omega. The Fourier transform is always a complex number. That's why we have to plot its magnitude plot and a phase plot. So exponential function f of t is plotted here, and its a magnitude plot. You can find out a magnitude of f of j omega is 1 divided by square root of a square plus omega square. So that will come out to be like a inverted parabola, and its peak value at omega equal to 0 will be equal to 1 upon a. So magnitude will be falling on either sides like a parabolic function, and then its angle also can be found out, or phase of that complex number can be found out. Tan inverse of omega upon a is the phase of denominator, so phase of f of j omega will come out to be minus of tan inverse of omega upon a. So during omega positive, that phase will come out to be negative, and during omega negative, that phase will come out to be positive. As omega tends to infinity, it will become tan inverse of infinity divided by a. So tan inverse of sine upon cos, where sine is becoming infinite, and sine is becoming infinite and cosine is a positive value. So it will be actually pi by 2, where the sine becomes a positive value and cosine becomes 0 value. The angle will be tending to infinity. Then we'll find out the Fourier transform of delta t, which is the impulse function. So impulse function, we know it is existing at t equal to 0, and area under the curve, that impulse is unity. Directly we will not be able to find out this, but this can be viewed as a scanning function, because there is a multiplication of delta of t and e raised to minus j omega t, and its integration need to be found out. Actually, delta of t is a very thin slate, but area under the curve delta of t is equal to 1. That's why multiplication of delta t and e raised to minus j omega t and its integration will give you area under the curve e raised to minus j omega t at t equal to 0. So we'll get answer to be e raised to minus j omega t at t equal to 0, and that answer will come out to be equal to 1. So the Fourier transform of delta function will come out to be 1, and it won't it won't have any imaginary part. That's why it will be only a real f of j omega, which is a Fourier transform of delta t. Inverse Fourier transform of delta omega also we can find out. The Fourier transform of delta t comes out to be equal to 1. So we expect here that inverse Fourier transform of delta of omega will come out to be constant value. But instead of taking delta omega, we'll take inverse Fourier transform of 2 pi into delta omega, so that we'll get a very simple function as a x of t, which is the inverse Fourier transform of 2 pi delta omega. 2 pi delta omega will substitute in the equation of that synthesis, which is the inverse Fourier transform. So x of t equal to 1 upon 2 pi integration from minus infinity to plus infinity x of omega e raised to j omega t d omega. So we'll substitute x of omega to be 2 pi delta omega. 2 pi will get cancelled, and it will be again integration of delta function. So integration of delta function, as we can view as a scanning function, and that will come out to be e raised to j omega t at omega equal to 0. That will be come out to be e raised to j omega t at omega equal to 0. So x of t will come out to be 1. Or in other words, we can say that Fourier transform of 1 will come out to be 2 pi delta omega. Inverse Fourier transform of 2 pi delta omega will come out to be 1. Or in Fourier transform of 1 will come out to be 2 pi delta omega. Then Fourier transform of signum function. Signum function is defined as signum function will be having value -1 for t less than 0, whereas it will be having +1 value for t greater than 0. So signum function can be expressed in terms of your exponential function, where we know the Fourier transform of the exponential function e raised to minus at u of t. Its a Fourier transform is 1 upon a plus j omega, whereas Fourier transform of e raised to at u of minus t will come out to be 1 upon a minus j omega. So signum function can be expressed in terms of exponential function. Limit a tends to 0, e raised to at u of minus t plus e raised to minus at u of t. Why to use this simplification? Because signum function or our unit step function will not satisfy the Dirichlet condition. Hence, directly we cannot find out the Fourier transform of signum function or unit step function. Hence, signum function is expressed in terms of exponential function. And then we'll get limit a tends to 0, e raised to minus of e raised to at u of minus at. It will be leading to -1 value for t less than 0, and e raised to minus at u of t, it will be leading to +1 value for t greater than 0. So Fourier transform of e raised to minus at u of t, that is 1 upon a plus j omega, and Fourier transform of minus of e raised to at u of minus t, that will come out to be 1 upon minus of 1 upon a minus j omega. So as a tends to 0, the answer of first 1 upon a plus j omega will come out to be 1 upon j omega, and minus of 1 upon a minus j omega, that also as a tends to 0 will come out to be 1 upon j omega. So 1 upon j omega plus 1 upon j omega, 2 upon j omega. And here we can once again find out the Fourier transform of signum function. We can plot its magnitude and we can plot its angle. Its magnitude 2 upon j omega, it will be coming out to be hyperbolic kind of variation, 2 upon j omega. So for omega positive, it will be positive. For omega negative, it will be negative. But its magnitude is there. That's why it will come out to be hyperbolic kind of variation for positive omega as well as negative omega. And its angle will come out to be tan inverse of minus of tan inverse of omega upon 0. So sine is positive and cosine is 0. That means angle must be pi by 2. So minus pi by 2 angle will come out for omega positive, and plus pi by 2 angle come out for omega negative. Similarly, u of t we can write in terms of a signum function, which is our unit step function, 1/2 into signum function plus 1. So for t negative, signum function is -1, that value will come out to be 0, and for t positive, signum function is +1, that value inside the bracket will come out to be 2, and u of t will be equal to 1 for t greater than 0 only. So this is the expression for u of t in terms of signum function. And then let us find out the Fourier transform of u of t, because we know the Fourier transform of signum function and we know the Fourier transform of 1. That's why 1/2 into 2 upon j omega plus 2 pi delta omega, because 2 pi delta omega we saw that it is a Fourier transform of 1, and Fourier transform of signum function is 2 upon j omega. So Fourier transform of u of t will come out to be 1 upon j omega plus pi into delta omega. Fourier transform of unit step function cannot be evaluated directly because it won't satisfy the Dirichlet condition. Hence, it is expressed in terms of signum function and found out it's a Fourier transform. Thank you.